I'm going to present an artifact in ozone profiles retrieved from limb scattering observation, which is related to inhomogeneities in surface reflectivity. I want to thank my co-authors, and I'm going to indeed introduce this artifact using mostly OMP's limb profiler observations, and which is located in the tropical Pacific. And so I will we investigated some possible causes of this abstract, and we put this in relationship with the presence of reflectivity inhomogeneities along the line of sight of the satellite. And I will shortly have a look also at the effects on radiance. So, as I said, we used mostly observation from OMP's limb profiler, which were retrieved in Bremen using the Skiatron radiative transfer model. It assumes homogeneous atmospheric conditions along the line of sight, and here I'm showing two panels. On the top, total ozone column and global anomalies averaged over several years, and on the bottom, stratospheric ozone column anomalies, again averaged. And here on top we can see fairly homogeneous field, but when we look at the stratospheric ozone column anomaly, we see this kind of band-shaped artifact, which is located indeed in the Pacific tropical region around 5 degrees north. And we were interested in investigating more the origin of this, and which is particularly relevant for tropospheric ozone column. This I'm showing here several tropospheric ozone column products, which are derived with using the limb nadir matching technique, so subtracting the stratospheric ozone column from the total ozone column. And as we can see, we have a positive band-shaped artifact in the Pacific region, because we saw the negative artifact in the stratospheric ozone column. And on top it's IUP OMPs, and the middle NASA OMPs, and it's also visible in the Skiamaki tropospheric ozone column dataset. And this is indeed relevant because we are talking about a few Dobson uni, but it's kind of 10–20% of the typical tropospheric ozone column value. And to locate it better in the profile, we compare the OMP's profiles with the MLS observation, and we see, so on the left here it's in the Pacific, they are average in the Pacific, on the right in the Atlantic, and the largest discrepancy it's here in the 0–10 degrees north, where OMPS is underestimating the ozone number density peak. And also the spread, the standard deviation, is larger with respect to MLS, which is not affected by the artifact. And investigating a bit better the possible causes, we were looking at some retrieval artifact at the beginning, but we could not detect any artifact anomalies in the fit residuals, nor in aerosol extinction, but we noticed this highest stream of higher reflectivity crossing the Pacific, both in the visible and in the UV. And this is related to clouds, of course, because in the tropical Pacific region there is the intertropical convergence zone, which is characterized by a frequent presence of high clouds, and we have a sharp gradient across the equator, where in the south part it's less clouds and much at lower altitudes. And as you can see here in this plot from another paper investigating the precipitation climatology, the ITCZ is pretty stable during the year in this region, and it really crosses the stretches across the Pacific. So we add a closer look to the Pacific region. Here I'm plotting a cross-section as a function of latitude of the stratospheric ozone column from OMPS in red and MLS in black, and we can clearly see that whereas MLS shows up pretty constant values from the equator to the north, OMS show this kind of negative bias followed by a positive artifact, so a kind of first derivative shape. And when we superimpose the information about clouds and surface reflectivity, we notice that the negative dip, it's occurring right to the south of the peak in surface reflectivity related to the ITCZ presence. So and it's kind of, so this artifact, it's kind of proportional to the derivative of the surface reflectivity. So we wanted to explore more this dependence of the artifact on the distance from the tangent point to high reflectivity scenes. And so this is the typical geometry. We have the OMS instrument flying to the north, and so looking to the south, so that the line of sight is crossing over the ITCZ region. And here I'm showing the tangent point and 1 degree latitude ticks. So we analyze then the surface reflectivity from OMS Nadir mapper to have a better resolution, and we try to classify the ozone profiles, requiring at the tangent point to be clear, so it's a low reflectivity, so less than 0.2, and we were looking for profiles that have a high reflectivity at some degrees north with respect to the tangent point. So we took into consideration 8 years of OMS data in the July-September period, because we saw this stable MLS background stratospheric column in the Pacific sector and in this 5 degrees south, 20 degrees north window. And then indeed we shifted the so to say reflectivity pattern requirements to the south until we found some profiles with a clear tangent point, but high reflectivity right to the north. And this is the effect in terms of ozone profile when we average all the ozone profiles in the different categories. We see that the artifact is becoming stronger as the high reflectivity bin approaches the tangent point, and in terms of ozone difference, we see that we have the maximum at around 2 degrees latitude north, and yeah, the line at 1 degrees north, it's not so relevant because there are not so many ozone profiles that actually fall in this category, but this is an artifact of about 5-7% difference at around 25-30 kilometers. And another way to see that, we try to constrain a bit better the reflectivity pattern. So we were trying to ask for a 2 degree bin high reflectivity to the north of the tangent height, and then shifting this pattern from the near field of OMS to the far field of OMS, so passing over the tangent point, and again repeating the same classification. And this is better. So the results in this case, the reference is the tangent point value, so exactly when the high reflectivity is on top of the tangent point. And so we see this sharp transition with a negative difference with respect to the reference case when the cloud or the high reflectivity scene is in the near field of OMS, and going to the positive values when it's in the far field of OMS. And this is also very clearly seen in terms of stratospheric ozone columns, when we average again for each classes again the SOX. And so this orange line in orange box refers to the case at the tangent point, and so on the left it's just the stratospheric ozone column values, and on the right the difference with respect to MLS. And we see indeed that the largest negative values are in the cases with high reflectivity values around 2-3 degrees to the north of the tangent point, and we see that the magnitude it's even larger than 10 Dobson unit, which is kind of it's larger than the average artifact in the whole data set, but it's kind of consistent to what we found before. And finally, we also had a look at the impact in terms of radiance. So I was considering the triplet that NASA is using for the retrieval in the visible, combining strong absorbing wavelengths with less absorbing wavelengths. And so this again, I took just all the level 1 data falling in all the categories that I presented before, and then so averaging the triplet profile for each category, and then we see that as soon as with the approaching high reflectivity beam to the tangent point, we see this bias. So the triplet goes to higher values. The reflectance is a clear case, so where there are no clouds along the orbit, and on the right it's the relative difference with respect to the clear case. And we see that actually this triplet is usually used up to around 30 kilometers, but it's change on some percent between 20 and 30 kilometers. And so this means that this reflectivity inhomogeneity produces a wavelength dependent artifact, so to say. And so in conclusion, we identified this artifact, and we kind of related to the presence of cloud of high reflectivity scenes in the near field of OMPs, and we saw also some effects in the triplets, so in the radiance itself. And the next step, which is actually very important, because then we need some relative transfer model simulation to actually verify that this effect is reproduced by our RTM, which can take into account changes in reflectivity, variations in reflectivity along the line of sight. And so there is the need actually to prescribe surface reflectivity from nadir observation to constrain then the retrieval, and there are some promising first result from Glenn. So yeah, thank you for your attention, and I want to acknowledge my funding agency.